So this is the last part of lecture 23. We're going to talk about time evolution of the model universe. Okay. Uh, Here's the section in the book. Uh, we're going to use Friedmann equations and the equation state to find the time dependence of the scale factor uh, and for a definite value of uh, curvature. So once you know what kind of curvature you have, you can find out what kind of how the universe expands or contracts. We're going to do a sort of model universe, assume a single component universe. Okay. So we're going to study the density behavior as the scales. Okay. Whether A increases, how the rho depends on A, basically. We can first, by differentiating the conservation relation. Remember, here's dE equal to minus P dV. Here's the energy, here is volume, and here's pressure. If you differentiate that, and if you're holding a fixed differential rho, so you have rho dot c square, and then I can divide out a cube, uh, leave a cube there later, and then on the on the on the then a differential rho c squared fixed in the a, so you have a factor 3 and a squared. Okay. And it's here, of course, p differential will be a, same as a square and a dot. So if I divide by a cube both sides, then this is just rho dot c square minus, both have minus 3, and from here I have rho c square, and from here I have p. Okay, and both multiply a dot over a. Now we substitute the equation state the fact p is equal to the parameter w times rho c square. So therefore, this p is equal to w rho c square, and factor out rho c square on both sides, and then on the left side just rho dot over rho, and the minus 3c plus w a dot over a. Rho dot, of course, rho dt and a dot dA dt, and I can get rid of dt, so therefore this is the same as say d rho over rho is proportional to dA over a, which is proportional constant. And I integrate on both sides, so each becomes log rho and log a with integration constant, and then I can undo the log by exponentiations, so therefore rho equal to the integration constant becomes rho naught a to the power minus a over this factor here plus w. So that's how the rho with scale with a depends on the what material you have, the equation state parameter w. For example, if I have a non-relative material and w equal to 0, in that case, rho scales like 1 over a cubed, that's expected. Rho scales like a volume, 1 over the volume. And for radiation, W is equal to 1/3, so this 2 over 3 and 3 cancel, so it's minus 4, so therefore the radiation density scales like a to the minus 4th power, and that's if it's not obvious to you, you can easily see, because this energy density, the energy itself scales like 1 over the wavelength, and so therefore scales like 1 over a, and then divide by the volume, 3 power volume, so therefore scales like 4 power in the denominator. Okay, so that's explain why radiation scales like a to the minus 4th power. For the special case, if the W is equal to minus 1, in which pressure is equal to minus of the energy density, in that case, of course, this factor just 0, so therefore rho is constant. So therefore you have a constant density, a constant energy density, for example, even though the universe expands, even though the volume changes, but the density do not change. And you will see that Einstein's cosmological constant, which we'll talk next time, and newly discovered dark energy have just this property. Now, remember we already mentioned that we actually turn out we live in a flat universe, so the k equals 0 is particularly relevant for us. So let's talk about this case. So Friedmann equation, if I set k equals 0, just get rid of the second term. And in fact, we know from the last slides, the rho scales like a to the minus 3, 1 plus w. So therefore, the a dot over a squared equal to a power over 3 rho dot a to the minus 3, 1 plus w in exponent. Now, let's assume that a dependent on times is like a power. So a is equal to a over a t naught to some power x. We don't know what power is, but it's some power. Okay. If that's the case, of course, you differentiate a dot, you get x times t x minus 1. So therefore, that combined with factor a in the divided. So a dot over a is just x over t. And from this relation, we can see you can relate the energy, relate the age of the universe, T naught, in terms of Hubble time. Remember, Hubble time is 1 over H naught. So, because H naught is A dot over A evaluated at T naught. And so, therefore, this relation tells me just T equal to T naught. So, therefore, T naught is equal to H over H naught. But 1 over H naught is just Hubble time. So, therefore, uh, the age universe equal to x times Hubble time. Okay. Now, if I substitute this into this relation here, a dot over a is x over t. So the right hand side is time dependent t to the minus 2. On the right hand side, a goes like t x. So the minus 3x, and both sides had to match. So it was the time dependence, t dependence on the left hand side is minus 2, and the t dependence on the right hand side is minus 3, 1 plus w times x. They must match. So therefore, I can relate x as 2 over 3 plus w. Okay. Now, knowing this, for example, knowing these two relations, we can suppose we say for a model universe that have an age that's less than Hubble time, which means x is less than 1. Okay, you plus x less than 1, then you can immediately show if this is less than 1, then w must be greater than minus 1/3. So in order for universe age less than Hubble time, the equation state parameter must be greater than minus a third. Otherwise, of course, is if it's less than 1/3, you have age greater than Hubble time. Remember, we already said for an empty universe, you can expect age to be Hubble time, and for a decelerating universe, you expect it to be less than Hubble time. And so all these can tie together. So for a matter-dominant universe, which means the W is equal to 0, then of course the X equal to 2/3, and then the, the scale factor scales the time to the T to the 2/3 power, and then if X equal to 2/3, so therefore the age universe is 2/3 of of Hubble time. Okay. For a radiation dominant universe, W is equal to 1/3, then X plug 1/3 here, and the X equal to 1/2. So therefore, in a radiation dominant, the scale factor depending on time is like to the power 1/2, and the age will be 1/2 the Hubble time. Now, remember we talked about the special case of W minus 1 when the pressure is exactly equal to negative the energy density, uh, and then density is constant. So in this case, uh, this will vanish, so x is singular, which means that our assumption that the scales like power is not valid. It turns out you will see in that case actually a scales like exponentially. Okay. Here we're talking about a case we assume k equals 0. Turns out this also is a good approximation for early universe, because early universe, because we're expecting a decelerating universe, and so a dot is ever decreasing as t increases, which means a dot is ever increase as t decreases. So when you go to smaller t, a dot actually increases. So this term dominate over this term, so effective we can assume the absence of the second term. So therefore, effective k equals 0. So so the k equals 0 is a good price for early universe, regardless of the value of k. Now, it's a good idea to, at least for a simple case, see how the universe will interesting how a depends on time. So I plot a as a function of cosmic time. Right now we're here with t naught, okay, and we know with time here, and we know the size of the universe, and we know the rate of expansion. So therefore, we know a dot here, okay. So now, remember we talk of for empty universe, the expansion rate is constant. So therefore, you get a straight line here, okay. And if for a closed universe, that's expansion will slow down until it stops and contract to from Big Bang to Big Crunch. Okay, and then for an open universe, it will decelerate, but uh, uh, but it will never stop. So therefore, they will keep going. And the flat universe between the uh, K0, it's just it will the expansion was slow, but it will never uh, it never will stop. Okay, unlike the so here we'll talk about the lessons we learned from lecture uh, 23. So the dynamics universe was determined by the Friedmann equation, which followed from Einstein equation, with Robertson-Walker geometry on one side and the ideal fluid source on the other. From the density and pressure of the fluid, these equations determines the scale factor of and the curvature k of the Robertson-Walker metric. Okay. The Friedmann equations have simple Newtonian interpretation, even though it's a relativity equation. And the first Friedmann equation is simply the energy balance equation. The second Friedmann equation is equation of motion, F equal to ma. Okay. For the this cosmological equation must be supplemented by equation state, which is defined to be pressure equal to some parameter W times the energy density, and for non-relative mass, W equals 0, for radiation 1/3. Okay. And for uh, for matter, rho scales like 1 over uh, uh, a cubed, which is expected from volume, and for radiation scales like a fourth minus fourth power, because energy itself scales like 1 over a. For a matter dominant universe, a depend on t like 2/3 power. Radiation dominant universe, a scales depend on t as half a power. In particular, k equals 0, matter dominant universe, the age is equal to 2/3 of a Hubble time. Okay, which will, this fact will be useful to know. For the next lecture, we're going to describe how Einstein introduced the cosmological constant in his field equation in order to obtain a static cosmic solution. The cosmic constant may be viewed as a constant vacuum energy density with a negative pressure, which gives rise to a repulsive force that increases with distance. A universe dominated by the vacuum energy expands exponentially. Okay, so okay, that's the end.